This is Honors Algebra 2 Precalc, section 6.4, Precalculus. We are doing dot products of vectors, and I'm on page 440 of the textbook talking about the properties of dot products. So, U and V and W are vectors in this situation, hence the reason I drew the little arrows over them. In the textbook, you'll see they're bolded, but again, bolding things in real live person where you're not typing is kind of the worst. So, hence the arrows for vectors. And C is a scalar, meaning a non-vector quantity. So, first property, u dot v equals v dot u, which is just saying that the operation is commutative, right? It doesn't matter which direction you multiply in. If you're doing a dot product, u dot v equals v dot u. Property number 2, if you do the 0 vector dot product by some other vector v or any other vector, you're going to get a 0, and that makes sense because both components of the 0 vector are 0, so you're multiplying things by a whole bunch of 0, and not surprisingly, you get 0. Notice the difference here that this is the 0 vector and this is just the scalar 0, the number 0. Number 3, if you have some vector u dot and then you do the sum of vector v and vector w, you can either do it as do the sum first and then do the dot product, or you could distribute that dot product and make it u dot v plus u dot w, and that's the distributive property. Property 4 comes in handy sometimes. If you do a dot product of a vector times itself, you get its magnitude squared. So v dot v would give you the magnitude of v quantity squared. And then the last one, if you have some, so this is fundamentally just multiplication, right? It's a number times a dot product, but they're all being multiplied. So essentially this is the associative principle. It doesn't matter if you choose to do it this way first, where you do the dot product first and then times by the constant, or if you want to do the constant times u and then bother to do the dot product with v, or if you wanted to put the constant with the v and then do the dot product with u. So it's essentially associative. It doesn't matter which order you put it in. So those are the basic properties of the dot product, and we're going to go ahead. I've given you 3 vectors. U equals 1 comma negative 4, vector v is 3 comma 1, and vector w is negative 2 comma negative 5, and we're going to find 2 things. First, we're going to find u dot v times w. Notice there's no dot there because it's not going to end up being a dot product, because u dot v is going to be a scalar. Scalar times a vector is not a dot product. And also, u dot 3w. All right, so let's go ahead and do this. I'm going to show you that there are actually, based on those properties that we did, there are a few ways I can do b. There's only the one way to do a. So for a, I'm going to go ahead and find u dot v first, right? So when I go to find u dot v first, I'm going to say, okay, u dot v means that this is, so this guy right here is going to be the product of the x components, which would be 1 times 3, so that's a 3, plus the product of the y components, which would be a 1 times a negative 4, so that's a negative 4, times this vector w. So that's going to be a negative 1 times vector w, which is a negative 1 times the negative 2, negative 5 vector, meaning that the answer here is a 2 comma 5, right? Notice that the answer is a vector, which makes sense because u dot v should come out as a number, as a scalar, and a scalar times w will be a vector. A scalar times a vector is another vector. All right. Now, for b, I have a couple different options, and I'll try and buy myself a little bit of room in a sec so I can do this a few different ways. So one way to do b is to go ahead and find what 3w is, right? So one way to do b is u dot 3w, and I could say, well, I know u is 1 comma negative 4, and I know that that's dot, and then 3w would be a negative 6 and a negative 15. So if I did u dot 3w, it would be the product of the x components, which is a negative 6, plus the product of the y components, which is a 60, and that's going to give me a 54, right? Negative 6 and 50 is 54. I'm not surprised that it's a scalar because my answer was a vector dot vector, and that should come out as a scalar. So that's one way to do it, right? But there's another way to do this, right? So let's say I didn't want to do it that way. Let's say I said, you know what, I want to yank the 3 out in front and just go ahead and do u dot w, which is one of those choices that was in the properties that we went through, right? Now, if I were you, I wouldn't mess with it. I'd be like, hey, I can do this. It's easy. I'm not going to rewrite anything. I'm just going to go with it. But if you had chosen to do it this way, you would have done u dot w. Well, if I do u dot w, I'm going to get a negative 2 plus a 20. So negative 2 plus a 20. But that 3 is sitting out in front, so that's a 3 times an 18. Oh, look, that's totally a 54, right? And actually, there's a third option if you totally want to be that weirdo. You could have just said, hey, I'm going to put the 3 with the u instead times this w, right? So 3u would have been 1 comma negative, or sorry, 1, come on brain, 3 comma negative 12, right? Times this negative 2 comma negative 5, right? And when I do my dot product, it would be the 3 times the negative 2, which would be a negative 6, plus the 5 times the 12. They're both negative, so they come out as a positive 60. And oh, look, it's a 54. So it didn't actually matter which way I did it. What I will say is it's way easier, like way, way easier, to do the one that you're handed rather than do a bunch of extra math.